A tree is a data structure that stores elements in the parent-child relationship. So, each node in a tree will have a parent, except root node. In this example we are using a tree with root node A. It has two children, left child is B, while right child is C. Node B has two children too, D, and E. Node C has three children, F, G, and H. Since D, E, F, G, and H don't have any children, they are called as leaf node, or external node. All nodes which are not external are called as internal node. They will have at least one child. In this tree, A, B, and C are internal nodes. Nodes which share a common parent are siblings to each other. So, B and C are siblings. But E and F are not siblings as their parents are different. Any part of tree, which can be further subdivided into another tree, is called a subtree. So, tree with root node, B, will form a subtree. There are two important attributes of a tree, depth and height. Depth is calculated for a node, while height for a tree or subtree. Depth of a node is the number of ancestors of that node, excluding itself. So, in this example, depth of D would be 2. Depth of C will be 1. Depth of I will be 3. Height of a tree is maximum depth of any node. In our case it will be depth of node I. So, 3. A binary tree is an ordered tree in which each internal node has exactly two children. So, each node can have either no children or one or two children. There are three basic operations on a binary tree. Left child will return the node on the left side of the current node. If there is no left child it will return an error condition. Right child will return the node on the right side of the current node. If there is no right child it will return an error condition. If current node is right child, then sibling will return the left child of the node. If current node is left child, then sibling will return the right child of the node. If there is no sibling, it will return an error condition. Let us see how these operations work on a sample binary tree. A proper binary tree is a binary tree, where number of external nodes is one more than the number of internal nodes. This is not a proper binary tree, because internal nodes are 2, and external nodes are 2. But this is, as internal nodes are 2, and external nodes are 3. This is not for the same reason, but this is. These are four important properties of a proper binary tree. In subsequent slides we will see explanation and proof of each of these properties. These properties are related with the number of external and internal nodes in the proper binary tree. So, you do not necessarily need to remember each of them at this juncture. Before explaining each of these properties, let us modify this tree a bit. We have seen, each node should have a left and right child. In case it is missing, it points to null. Now, we will do a slight modification. We will replace the null node by a special node, and that special node is called a leaf node. In other words, each null node is called leaf node. We already know what a leaf node is. It's an external node. So, we are still adhering to the definition of leaf node, as it is still the last node of a branch of the tree. Let's take a sample tree. In this tree, null children are we will replace these null children with a leaf node. And this is how our tree will look now. This restructure is just for simplicity. If you do not want to replace null node with a leaf node, then leaf node will be H, I, F, and G. Now, let's revisit the first property of a proper binary tree. The number of leaves are between 1 more than the height and twice the height. Let's prove this using the worst case and the best case of a proper binary tree with height 3. By worst case, we mean a tree having the minimum number of nodes, internal and external. And by best case, we mean a tree having the maximum number of nodes. So, at height 3, the worst possible tree would be, and the best possible tree would be. In worst case tree, number of leaves are 4, which is 3 plus 1. In best case tree, number of leaves are 8, which is 2 to the power 3, hence 8. So, the theory holds valid. The second property states, the number of internal nodes fall between height and 2 to the power height minus 1. Once again, we will prove it using the worst case and best case scenario with a tree of height 3. In worst case, the number of internal nodes are 3, which is same as height. And in best case, the number of internal nodes are 7, which is same as 2 to the power of height minus 1. Let's prove the third property, which states the total number of nodes fall between twice the height plus 1, and 1 less than 2 to the power height plus 1. One way to prove that would be by adding the total number of internal and external nodes, which we saw in previous 2 slides. But, let's also prove it using a tree of height 3. In worst case tree, total number of nodes are 7, which is twice the height plus 1. In best case tree, total number of nodes are 15, which is 1 less than 2 to the power height plus 1. Height of any binary tree is least 1 less than log of nodes plus 1, and at most, half of nodes minus 1. Let's prove it mathematically first. We already saw this in previous slide. Let's prove the first part. Now, let's prove the second part. So, we have proved it theoretically. Now, let's prove it using a worst-case tree with 7 nodes, and a best-case tree with 15 nodes. So, the worst-case tree has 7 nodes, which means height should be 3. In best-case tree has 15 nodes, which means height should be 3.